Day and welcome to TDPhysics. Thank you for joining me as we learn about relative motion in 2 dimensions, non-90 degrees. So our piece of history today is the Mark IIA calculator for course and speed. And this would have been used by the Royal Canadian Air Force and other allied pilots, particularly the navigators, to do a whole bunch of calculations that you've been practicing already and will practice, but it did it for them. Really neat physical calculator as opposed to a digital calculator that we might use today. And it was handy because it would do your calculations very quickly on the fly. Now, what do the different parts do? Well, on this dial, we get to see that there's the direction that we want to go. So that might be the bearing that we would be hoping to take. Over here, we have some information about the fluid that you're moving in, like water or wind. Wind, obviously, in the case of flights. And then we have a little corrector needle right here that lets you know what the correction should be. So you would tell the pilot, oh, I know you want to go 360, but you should actually aim that a few degrees to the right, or in this case, to starboard. And finally, we have an arm that comes down that will actually make all those pieces come together. You'll notice that as the arm swivels, the correction changes. So for example, if we were trying to go north and our speed, okay, which is listed on the side here, in knots, if you want to use that unit, or in miles, remember this is from the 1940s, then if that was your ratio of how fast you were going to how fast this fluid was going, then your correction would have to be a little bit to the right or to starboard. If our fluid sped up, so we were in a really big storm, well, suddenly the correction would have to be much more to the right or to starboard. So in today's video, we're going to talk about what happens when the wind doesn't point simply perpendicular to the way we want to go, but what happens if that changes. Now the wind is going against us and a little bit to the side. And so if that was our situation, we would have to correct about that much. Now we're actually going to play with that in a bit more detail as we get into today's lesson, but how far you have to correct depends on the direction of the wind, the speed of the wind, and ultimately there's a little lever on the side here that allows you to push it in, and that will change how fast you're going. So if the wind is going very, very fast and you are not, then the correction gets bigger and bigger and bigger. Finally, what's the resulting ground speed? Well, that's the little nib here will let us know. So we'll work on those things, but on paper. The role of navigator is always complicated because winds don't always cooperate and travel at 90 degrees to the direction you intend to travel. So targets, while they stay the same, winds change. And so this particular example is going to come from December 7th, 1941, when a number of aircraft carriers under Marshal Admiral Yamamoto from Japan, those carriers were moved within about 300 kilometers to the much lesser patrolled areas just to the north of Oahu. That's in the Hawaiian island chain. And he launched a large number of airplanes known as Zeros from there that could travel at about 540 kilometers an hour, a bit faster if they needed to. And the prevailing winds around there go from the northeast to the southwest at about 60 kilometers an hour. If the pilots had been unaware of that and hadn't corrected in their navigation, what would the consequences to that have been? So on my recommended scale here, 1 centimeter equals 30 centimeters. That means that our plane speed on this particular diagram is going to be directly south. And we are imagining that the pilots don't know that they're supposed to correct for it. And so on my scale right here, this is approximately, as close as I can, 18 centimeters down. The second factor here is that there are prevailing winds. And so we have to add those wind velocities to the plane velocities. So that on this scale, well, if 1 centimeter equals 30 centimeters, then this is going to be 2 centimeters off to the southwest. And so I have to get my angle in there just right. And this should be 2 centimeters at this angle. So those two velocities added together would give us a resultant velocity relative to the ground. So I'm going to take my scale diagram here and I'm going to add those two together. What we're going to notice here is that we're going to go a little faster than we expected, but a little off course. Something to the tune of about 4 and a smidge degrees this way. And so what we find if we use a scale diagram and do this very carefully, when I did it with my scale, the resulting numbers that I got, if my vertical side here was representing 540 kilometers an hour, and the one down here was equal to 60 kilometers an hour. And I guess this angle in here was 45 degrees. If we're going to be really fancy, the interior angle here would be 135 degrees. Although for that, if we're not going to do pure math, that's less important. And so our far side, if we stick a scale on this, I measured this out to be approximately, let's see, about 19.4 and a half, I don't know, almost that. And if I multiply it by 30, that comes out to approximately 584 kilometers an hour. And I fully recognize that if we're estimating this, what that's going to result in is for your scale diagram, it might be a little bit less if your line was a bit shorter, a little bit longer. In either case, it's about 580 and a smidge. So we'll go faster, but more importantly, what is the angle right here? And so when I was measuring that out with my protractor, I came to an angle of approximately more than 4, but not as much as 5. So I estimated it was about 4.2 degrees. Now, I cheated and put that into a calculator online, and it works out to 4.16 degrees, but about 4 degrees off. So what's the big deal? A deflection would be velocity of the plane relative to the ground would be equal to approximately 584 kilometers an hour. But more significantly, south 4 degrees west. So what's the big deal? If you were traveling just 4 and a smidge degrees off, but the distance you were traveling was approximately 300 kilometers, the amount that you would be out would be almost the width of Oahu. And those pilots were looking for a very specific path in. They had spied it out fairly well and had an idea where they could get the best surprise attack. If they had not corrected for this, they would have almost missed the island, being forced to spin around the island and attack from angles they were not hoping to do, losing the element of surprise, and losing the amount of time that they had available for fuel to do reconnaissance or attacks. And so they did not do this. So what did they do? Well, what they did do was correct for it. So we'll flip over the page here. Those pilots actually corrected for those prevailing winds. As a result, they pointed their planes slightly into the wind, so south 4.5 degrees east. But how can we prove that? Well, the first thing we're going to do is I'm going to use a simple dotted line here to represent exactly north-south. So the two vectors of the plane's velocity in still air plus the air's velocity have to start and end on this line in order for the plane to be traveling down that dotted line. So it's tricky with relative motion because the planes don't point in the direction that they're actually going. So let's set it up as a scale diagram first. I have a little less room here. I'm using a slightly different scale of 1 centimeter is going to be equal to 60 kilometers an hour. So in that case, my plane in still air is going to be 540, that'll be 9 centimeters. And the air is going to be 1 centimeter. And I know everything about the air, so I'm going to start with it. Another way of looking at setting this up is what direction do you have to point the plane at to land in the air that's going to be moving to where it's going to be by the time you get there? Because the air that you're aiming at is going to be moving. So let's try that. So I need to draw a line that's 1 centimeter long that ends on this line and goes at 45 degrees. Here's my best shot at that. Okay, so I'm going to draw a line that is 1 centimeter long. That is going to go from, well, somewhere out here right up to the line. I'm going to be using a ruler sitting on top of my screen here for length, and then I'll use my onboard protractor to measure that angle. Okay, so that is the length of the line, and sometimes the computer is a little fussy when it comes to putting vector arrows on, but that's the best job I'm going to come up with. Now this next part is a bit trickier. So this is the velocity of the air relative to the ground. Remember, that was 60 kilometers an hour. Now our next one, I'm going to have to start over here and end over here. Now I don't know exactly where that's going to be, but I know that when I put my ruler on here and get something nice and tidy, this length right here is going to have to be 9 centimeters. So I'm going to make way for a nicer version of that. We'll solve this using skill first, and then we'll try to do it with some pure math. Okay, so here's my line. We'll use a slightly different color for this one. So I need to have it connect here to here. And now what you can't see off screen is that sitting on top of my monitor right now, I've got a ruler, and I am stretching that ruler out until 9 centimeters comes and touches my red line. Now that happened to touch the red line right there. I got lucky on that one. In that if 9 centimeters had needed more line, I would have had to go back and extend it. So here is what the pilots are aiming at in blue. So our pilot's velocity in still air, sometimes we call it the plane relative to the ground. So that was 9 centimeters, and this one was 1 centimeter. And so when we do some measurements on the other side, I'm putting my ruler now on my screen. What I should come up with is something, let's see. So again, you can't see, I'm off screen. I'm carefully putting my ruler on my screen right now and measuring this to be a almost 9.7. So my scale, this was just under 9.7. I'm going to say I'll say 9.7. It's hard to measure anything more accurately than that. And if I multiply that by my scale, it comes up to approximately 581 kilometers an hour. So they actually speed up, and the direction of this is directly south. Now the one thing I need to measure here is I need to find my angle. Again, on screen or off screen, you can't see it because it's physically on top of my screen right now. I'm measuring this angle with a protractor to be, I'm just going to call this 4.5 degrees. So in our previous problem, remember it was about 4.2 degrees that they would have ended up being blown off of course. So the correction isn't exactly that direction on the other side of south, but it's close, especially if you're a fast airplane. So I know there's some people in the class that love pure math, and they're looking at this saying, well, this isn't all that great, to be honest, because it's a scale, it's plus or minus a little bit. So if we want to do pure math, if you don't want to do pure math, skip ahead until you see question number 3 being started. Well, we know this angle right here is 45 degrees, and we know that our sides on this one are 540, and down here they are 60. The ones that I'm highlighting in yellow, we know because they have been given in the problem. The other ones over here were based on scales, so we don't actually know the ones that have been boxed in here. We're going to test that with pure math. If we've been careful, it should be very close. Is this a right angle triangle? Definitely not. So we can't use sine, cos, tan. We can't use Pythagorean theorem. What we can use, though, is sine law. So sine A over A is equal to sine B over B. We're going to go check our answers with some pure math. So I'm going to call this one A. So that means that this side is A. I'm going to call this angle B. So this side is B. And so that, by process of elimination, makes this angle C and this side C. Let's do the A's and B's first. So sine of A, that's what we're trying to look for. That's our special angle up here. The opposite side of that is a 60. So that's down here. Angle B, we know that is 45 degrees. So that is equal to sine 45 degrees. The opposite side to our 45 degrees is 540. So if we punch that into our calculator, sine of 45 degrees is 0.707 times 60 divided by 540. Remember, because the 60 comes up top, just multiplied both sides by 60. And so if we're going to find A is going to be the inverse sine of everything that's inside this box. So 0.707 times 60 divided by 540 is 0.0786. We take the inverse sine of that, we come to 4.5 degrees. So that matches up with what we have right here. And if we did that further, did some more testing, we could use sine law again to figure out our side C. Well, angle C, remember that a triangle is equal to 180 degrees. So if we minus our 4.5 degrees and we minus our 45 degrees, then what we're left with is the leftovers from that. So 180 minus 45 minus 4.5 gives us 130.5 degrees. So that is our angle C. If we go through the process of what we've done here before using sine law, so sine A over A is equal to sine C over C. So this is all getting a little crowded right here. So we'd have to do some cross multiplication. So C is going to be equal to sine C times A over sine of A. So C is equal to sine of C, which was 130 degrees, divided by sine of A. Remember, that was 4.5 degrees, times A, which was equal to 60. So we punch that through, that comes to 581. So those two methods match. So you can use pure math, you can use scale diagrams, both are good. Okay, so their official correction, they'd have to aim their planes a little bit, 4.5 degrees specifically, to the east, and that would allow them to travel due south. Finally, how long is it going to take them to get there? Well, these calculations are used all the time. Every time you get on a commercial plane, they estimate wind speed, what the plane is able to do, also how angry the passengers might be. They'll try to save fuel if they can, but if they're behind on time, sometimes they'll pay a bit more for fuel cost to ensure that customers are happy in the end. Number 3, what's the resulting ground speed and how long did it take them to get there? Well, the important thing for working on this is that you always cancel out vectors in the same direction. So again, the example I use in class is that I live 45 kilometers north, a little bit towards the east of our school here in Woodbridge. But if I drive south, well, the question, how long does it take me to get home, doesn't make any sense. I'll never get home. We have to make sure that our directions line up. So if time is equal to distance divided by velocity, our distance was 300 kilometers towards the south between the aircraft carriers and Pearl Harbor. The velocity, well, it ended up being a little bit faster, 581 kilometers per hour. That was also south. Because these are both south, they cancel out, and that works. 300 divided by 581 works out to 0.516 hours, or thereabouts, about a little over half an hour. So when those planes launched, radar systems on Hawaii did pick them up, but communications issues, in spite of the best efforts of some of those radar controllers, did not get through, and signals were ignored, and as a result, the surprise was essentially complete, and the devastation similarly quite bad. So, a difficult piece of human history, but an absolutely essential example of why being aware of relative motion is essential for traveling in any fluid. Large planes like the Halifax bomber you see in the background behind me and my Uncle Ted here had a navigator whose full-time job was to make sure that the plane got where it needed to get. My uncle fixed engines, the Merlin engine, like the ones in this plane, also found in Mustangs, Lancasters, Mosquitoes, Spitfires, Hurricanes, some of the legendary names of World War II aviation. He could tear them apart and put them back together like no one else, and I'm going to miss him terribly. So thankful for his service throughout all of North Africa and Italy and the Western Front, and in peacekeeping missions thereafter. Thank you for your service.